Hello students, this is Govind sir, and today we are discussing the next topic of unit second, that is modeling of systems. We have different type of modeling of systems like mechanical systems, electromechanical systems, fluid systems, thermal systems. So in this lecture we will model the systems. Okay, so let's start with the mechanical system, modeling of mechanical system. So we have two types of mechanical system. One is translational mechanical system and second one is rotational mechanical system. In the translational mechanical system, the movement is done along a straight line, or can say translational mechanical system move along a straight line. These systems mainly consist of three basic elements, that are spring, mass and dashpot or damper. So we will discuss about these elements of the mechanical system broadly in the next slides. So main thing is the classification of mechanical system on the basis of their movement. First one is translational mechanical system that move along a straight line. Okay, another one is rotational mechanical system. Rotational mechanical system move about a fixed axis. Okay, there is a movement about a fixed axis, and same there are three main basic elements are present, that are moment of inertia, torsional spring and dashboard. We will discuss these also in the next slide. So let's start with the basic element of translational mechanical system. The first one is mass. Mass is the property of a body which stores kinetic energy. Okay, now zoom it. You can see in this image there is a body which has a mass m, and we have applied a force F in this direction, and the movement of x is the same direction. Okay, so according to the second law of Newton, that is, the force opposes the applied force, that is Fm, is directly proportional to the acceleration of body. So Fm is directly proportional to A. That we have Fm equals to Fma, where is m is mass of body, A is acceleration, and m is the force due to the mass. So we got the equation, that is Fm equals to m d square by d square x upon dt square, that is in the form of displacement. X is displacement. Okay, but this generating force, this opposing force is directly equal to the that applied force, because the Fm is applied in direction and the applied force is applied in this direction. Then at the equilibrium condition, or can say in the free body diagram, these two forces are equal. So F equals to Fm, that we have F equals to m d square x upon dt square in the form of displacement. So this is all about the mass equation. Okay, now we have another element, that is spring. Spring is an element which stores potential energy. Mass stores kinetic energy, whereas spring stores potential energy. So we have seen in the figure, there is a spring, the one end is rigid on the wall and the another is free, and we have applied a force F to this direction, and the displacement we have x in the same direction. But the spring opposes the applied force, and that opposing force is directly proportional to the displacement. And then we remove the proportionality constant, then we have Fk equals to Kx, where K is stiffness constant, and this opposing force is directly equal to the applying force in the equilibrium condition. Okay, and in the stretching or in the compression situation, the spring stores the potential energy. So it has energy in the form of potential energy. So F equals to Kx. So this is about the spring equation. Okay, now we have another element, that is dashpot. Dashpot is also named as damper. If a force is applied on the dashpot, it is represented by B. Okay, then it opposes, it is opposed by an opposing force due to friction. So we have an opposing force due to friction, and that opposing force, you can see in this image, and we have applied the force in this direction, and the similarly we have the displacement in the same direction. Then the friction opposes this applied force, and that opposing force is directly proportional to the velocity of damper. Okay, so we can remove this proportionality constant, and we get Fv equals to Bv, that B is a friction constant for damper. Okay, and we have Fv equals to B dx by dt in the form of displacement. Okay, then the final equation for the applied force is equals F equals to Fv. Fb is opposing force of damper, and equals to B dx by dt. So these are the basic three elements of modeling of translational mechanical system. Now we have a rotational mechanical system. In this also we have three basic elements. First one is moment of inertia, where in the translational mechanical system we have mass, but in the rotational we have moment of inertia. The same thing is, both stores the kinetic energy. So we have moment of inertia J, we have applied torque T in place of force because it is a angular force, and we have a displacement of theta, that is angular displacement. Okay, so the applied torque and the applied theta, there is a relation with the torque produced by moment of inertia. So moment of inertia, the torque of moment of inertia is directly proportional to the angular acceleration. Alpha is angular acceleration, and when we remove the proportionality constant we have J, that is moment of inertia. So Tj equals to J d square by d square theta by dt square, where is theta is angular displacement. Okay, then the opposing torque is directly proportional to the directly equal to the applying torque. So T equals to Tj, then T equals to J d square theta upon dt square. This is for moment of inertia. Another element is torsional spring. Torsional spring stores potential energy similar to the translational spring. It also stores the potential energy, but in the form of angular displacement. Okay, so a spring, one end is rigid to the wall, and we are applying torque, and there is a angular displacement, that is theta. So the opposing torque of spring is directly proportional to the theta. Similar to translational, there is F is directionally proportional to x, but x is translational displacement, but and here is theta is rotational displacement. So Tk is equals to k theta. K is stiffness constant for spring, and the applying torque is equals to opposing torque Tk, that is k theta. This is all about the torsional spring. Okay, now we have another dashpot. If a torque is applied on dashpot B, then it is opposed by an opposing force due to the rotational friction of the dashpot. In the translational we have a just friction of the dashpot, but here is we have rotational friction of the dashpot. So rotational friction torque is directly proportional to the angular velocity. Omega is angular velocity. Okay, so Tb equals to B W, that is B omega, and it is defined in the terms of angular displacement, that is B d theta upon dt. Okay, so opposing or rotational friction force is directly rotational friction torque is directly equal to the applying torque in the equilibrium condition. Okay, so we have the equation for dashpot, that is T equals to TB equals to B d theta by dt. So these are the basic elements of rotational mechanical system, and we write the equations for these